Welcome in. So the subject is CORTECONs, content-retentive, temporally connected neural networks, as it has been for the past few YouTubes. Before we get into the meat of today's material, which is the beginning, the first steps of a walkthrough of a ultra simple little example, but one that can take us from start to finish. So as a quick contextual note, we've already had the first step in going through the code. And this is the second gen code. It's the object-oriented code. We don't need object-oriented for right now, but we do for later algorithms. So let's get the foundation started right now so we can work with it later. Secondly, we've already had a video that overviews the architectures and the equations. As we look at the equation for the cluster variation method, which is an integral part of the CORTECON architecture, we understand why perhaps that equation has not been very popular. It's a little bit big, it's a little bit complicated. The code, as we've already been noticing, will certainly continue to note as we build out all the steps. The code is a bit complex, and we're still just looking at the 1D version. Things get interesting when we move to two-dimensional. That's where the excitement begins. But let me just suggest this is by way of an analogy. Suppose that we want to swim out in a large bay. Actually, let's make it out in open water. And we don't know how to swim. So the first thing that we do is establish sort of a little perimeter with guy wires around an enclosed area. And we put on water wings. Now I'm making up this analogy as I go along because I don't swim. Now we're out there in this very safe, protected environment. We're not going to sink and we're not going to drown because we got water wings on us, and that's the one-dimensional version. It's a much safer, more protected, easier environment. Secondly, we're holding on to a guy wire. What that means is, for all of our examples for the reasonably near future, we're going to set the requirement that we have equal numbers of on and off nodes. What that does is make it possible to have an analytic solution. And an analytic solution is our safety guy wire. That gives us a sense of confidence, as in, okay, my computational results are giving me certain values, and yes, they correspond more or less to the analytic, to the predicted. And that's going to give us some comfort and security, because the next step will be to venture away from the guy wire. So for these next few vids, we're going to be going through that one example where the requirement is that we can compare our results to analytic. That'll be such a gratifying feeling, and there are numerous steps involved, so we want to be sure that we can trace everything cleanly and clearly through. We're not going to get it all done today. Today we're actually just going to be counting up configuration variables. I am so begging your indulgence at the beginning, because if you thought that going through the code walkthrough was a little tedious, counting the local configuration variables is very tedious. And we're going to go through it because, yes, of course, you can just put it all into the computer program. We can transcribe our little very cutesy, short text string that we're going to use into the code, hit the button. It's like, okay, these are my results. But what we're after right now is getting a sense of intuition, a sense of comfort, a sense of being able to visually look at a grid, whether 1D or later 2D, and say, okay, I know what these clusters are, and I can eyeball, I can get a guesstimate, I can get a gut feeling for what my local configuration variables are. That is going to be so important as we progress. So here's why we're doing this now, and why I'm actually sort of putting a little push on. I've been up since crazy hours of the morning and working very much around the clock to bring this to you as fast as possible. And this is why. First of all, we know that we need to move beyond what we've got. If the current rage is all generative AI, and that's a lot of fuss about autoregression, there's really not much under the hood there. So the reason that people haven't moved on perhaps more rapidly is we haven't known exactly what equation to gravitate towards. We need that. This offers us an opportunity. So it's very well timed in the evolution of AI systems. Secondly, there's enough done right now so you can come on in, and even with just the materials that we've offered so far, you can grab the code, nascent though it is. You can grab the concept that we've been presenting in the architecture and equations vid. You can take this as an example, push on through. If you had to, you could do it completely on your own. Not as much fun, certainly. It's always more fun to be able to follow somebody's lead, check your work, and get some insights along the way that might otherwise take you a little while. But you know what? There's enough done now and there's enough shared already that the time is right. We can do this thing. Here's the third reason, the most important, the most compelling, the most exciting and satisfying. We want to do AGI. We know we're not going to get that out of what we've got on hand. The equations aren't going to support it. So the time is right for something that could possibly take us to the new level. So with that, I'm going to close this intro. I've been up since crazy early putting slides together. I was doing the same yesterday. This is evolving at breakneck speed so that you can get your hands on it as rapidly as possible. So before we get started, let's do a quick review of our CORTECON basics, just for those who haven't had a chance to watch the preceding two vids that gave the code walkthrough for the first local configuration variable, wleft, and haven't seen the architecture and equations vid either. So we're just going to sum this up very quickly. CORTECONs, standing for Content-Retentive Temporally-CONnected Neural Networks, are a new class of architecture, so there are a lot of possibilities and permutations. However, the single most consistent element in a CORTECON is that the internal layer is a 1D or 2D grid with a pre-established structure, and the nodes in that grid come to a free energy minimum. That is, we can periodically tweak the activations of different nodes, allowing the grid to move to a non-equilibrium state, and then we invoke a free energy minimization process, bringing it back to equilibrium. This is a separate process from the usual weight training that we see in most neural networks. During the training phase, we can alternate presenting the training data and adjusting the vertical connection weights, as is typical with most neural networks, with a free energy minimization process, which would involve changing the activations on the internal latent layer, the cluster variation method grid layer inside the CORTECON. Now there's a whole lot more that we can go into. There's a lot of subtleties and nuances to this process, but let's reserve that when we can go back to the architecture and the processes. Today we're just giving it the quickest of overviews. Let me briefly move on to the notation used in this slide. If you see the action layer and the sensory layer at the top and bottom respectively, those correspond to action and perception or sensory nodes that are originally envisioned by Carl Friston in some of his work. The psi, that's Greek capital letter psi at the bottom, refers to the external world that provides the inputs to the sensory layer. We'll pick up on this discussion of notation once we get back to an architecture discussion. That will be an entirely different vid. I began using this notation early in the reinvention of CORTECONs beginning around 2016, with the idea of using CORTECONs as a method in Carl Friston's active inference. That's been a crucial element of the design process for this reinvention of CORTECONs in this era. Now before we go on, I'd like to make a point with you. In fact, it's so important that I set up camera and we're shooting a little extra vid. So it's actually 2 points. First of all, when you interchange any two nodes that are of different activations in this CORTECON cluster variation method grid, I'm going to just start calling that the CVM grid for short, and it can be 1D or 2D. When you interchange nodes that have different activations, you change the entropy of the system. This is radical, this is new, this is different. This is especially different if you're used to thinking about entropy in terms of the way that we usually talk about it in neural networks. So for example, if you've been studying Hinton's work on Boltzmann machines and you've read the contrast of divergence paper and you've read some of the other really great classic works on how to use Boltzmann machines and deep layered architectures. And they present an energy equation, which I would call an enthalpy equation, but hey, I'm a physical chemist. They're coming from a physics background, slight difference in wording, and it's just the difference, say, between French and Italian. But they're presenting what they call an energy equation, which has activation enthalpy, energy, and interaction enthalpy, energy, same thing. And when it comes to the entropy, they don't even use the word entropy. They make this like hard right turn, and they go into talking about Gibbs sampling, Monte Carlo. In other words, the entropy term that's needed is very subsumed. It comes about through creating the data set. And once it's created, you never change the entropy because it's a function of the distribution across all possible states. Entropy does not have any parameters associated with it at all. And even with what we're introducing, entropy is parameter free. That's the nature of entropy. Parameters are all over in the enthalpy term. So when you start setting up in a Boltzmann machine, in a deep learning architecture, all these different connection weights, and by the way, same thing in transform. What you're doing is you're modifying the enthalpy/energy term, and you keep refining and twitching and teasing these little parameters until you get desired results. What we're introducing is this new mechanism by which you can change the free energy of a system by interchanging activations of nodes that impact the entropy and not just the enthalpy. So radically different. Second important point, again, really super important, and it's this. The entropy term, that is that one-dimensional or two-dimensional, so much preferably two-dimensional, because then you can see connections between clusters, you get interesting topographies. It's so much more exciting, but hey, right now, we've got the water wings on, we're doing 1D. Back to the main point. That grid, that 1 or 2D CVM grid, is not necessarily representational of activations in a spatial configuration in the physical environment. In other words, it's not like a masking field in a CNN. It's not that. This is an abstract layer. The nodes themselves can mean anything, especially when you're starting off your training, they can mean anything. They're as abstract as any within the Boltzmann machine, for example. Later on, as you train and as you play with the clustering parameters, the epsilon 1 particularly, to force clustering, you will likely arrive at nodes where neighboring nodes take on representations for the same or very related patterns, that is in the input. They become feature detectors for the same or similar things, but that is not necessarily tied to something on the physical plane. Now, I'll show you examples down the road where we are creating a model, the CVM grid, that is somewhat, especially initially, identifiable with an initial physical layout. So the model and the representation start off the same, and then we adjust the model because we're going to bring the model to a free energy equilibrium. And this is going to be a few vids from now. We're not there yet. It's going to be a 2D grid. It's going to be related to a very tangible thing so we can get a good gut level sense of how this thing works. But keep in mind, our 2D grid, or even our 1D, lives within the abstract realm. This is a latent space. Okay, back to our main discussion. Oh, one further point. When you see me flip nodes in this little example that we've used in the code walkthrough for the 1D grid, and we're going to pick up with that example because we certainly haven't taken it to its conclusion. But when you see that, we're going to interchange two nodes and you're going to have the opportunity to do this. That's going to give you actual hands-on experience of seeing the entropy shift as you interchange nodes, and won't that be an interesting thing? It'll be so much fun. Okay, back to our main discussion. There are 5 steps to the process that we'll use to demonstrate how to use the cluster variation method. The first thing we're going to do is create a short little text string, and we'll identify the consonants and the vowels. They need to be equal in number here to make the analytics work. We'll identify those consonants and vowels and place them onto a single zigzag chain for the 1D CVM grid. We're going to then compute the configuration variables and the entropy for that grid. Once we have our configuration variables, we're going to consult the analytic solution. Specifically, we're going to identify what the interaction enthalpy parameter would be for 3 crucial configuration variable values. We'll use the dispersion for the resulting set of interaction parameter values to identify how closely these configuration variables are aligned with an equilibrium state. Now, as a third step, we'll use the 2 extreme values to identify a test range for finding the most suitable interaction enthalpy. Our fourth step will be to use that range and step through an incremental series of different interaction enthalpy parameters to identify the free energy associated with each. And then finally, as a fifth step, we're going to use a new divergence measure that I've created. I'm calling it the Kikuchi-Marin divergence, to find the enthalpy parameter that gives us the best free energy match for our test string example. Now, if this sounds like a lot, I assure you it is. And we're not going to get through it all today. We're going to focus right now on just those local configuration variables. So let's start with our text string, which is, please like me on Facebook, thank you, and please, personally, don't like me on Facebook, I don't ever go there. But I needed a simple, short little text string that was largely a consonant-vowel combination, one after the other, and that's more or less what we have here. Oh, by the way, I'm cheating just a little tiny bit. In the English language, we typically regard Y as a consonant when it begins a word, but I'm using it here as a vowel, simply because I had to fudge things a little bit and get that even number of consonants and vowels. Now for our depiction, we're making the vowels be dark and the consonants be light. So if we ever worked with a language such as German, with more consonants than vowels, we'd see the vowels floating like dark islands against a sea of white consonants. Now in the right-hand side, during these past few figures, you see in a column of Z values, Z1, Z2, etc. Those are the various kinds of triplets, and we'll be going through them shortly. As you've noticed, there are 6 different kinds of Z triplets, Z1 through Z6. Z1 represents a set of on units, or vowel, vowel, vowel. We've only got one of those in our data set. It's at the very end in the word U, Y-O-U. We're once again retreating that Y as a vowel for purposes of this little demo. We have 8 instances of that next triplet, the Z2s, and a quick word on notation. First, I'm using capital Z's to reference the exact count. We're going to use small z's and in fact small letters throughout when we denote the fractional variables. Secondly, you'll see that I'm multiplying that z by a factor of 2. That's the degeneracy factor, and it means that we can count our z2 2 different ways. We can count vowel, vowel, consonant, or consonant, vowel, vowel. So I'm multiplying the z2 by 2 to reference that, and you'll see that when we get into the analytic equations. We're going to count our z2 values, starting with a vowel, vowel, consonant triplets. We're looking for situations where we see 2 dark units, those are the vowels, on a close diagonal with each other, and then the next diagonal would be a light-colored unit for a consonant. Now we can easily spot 3 of the vowel, vowel, consonant triplets in this, and then to find a 4th, we look at the very end of the chain where we see the U-O from the U, and then the P, which is a wraparound to the P at the beginning of the phrase. So we found 4 of the vowel, 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 consonant Z2 triplets. Now let's go hunting for the consonant, vowel, vowel, and we easily spot those. Now let's count those Z3 triplets, which are the vowel, consonant, vowel. We've got 6 of them. The first one's easy to spot, and then a little down the road we can find another, and then the remaining 4 all overlap those. So it's a little complicated to see here. I'll put a copy of this figure on the blog post. It'll be easy if you want to check your work against mine. We're at the halfway point, and we can wrap this up pretty quickly. The Z4 triplets are the consonant, vowel, consonant triplets, and there are 6 of those. And now that you understand how to do it, it'll be easier for you to work that out on your own. Once again, putting a copy of this onto the blog post in case you want to check your work. The Z5 triplets, just like the Z2, come in 2 types. Here we have consonant, consonant, vowel, and vowel, consonant, consonant. Once again, there are 8. I'm showing this to you in 2 different slides, and again, they'll go in the blog post. Our last task is to look for the Z6 triplets, consonant, consonant, consonant. And it turns out there's just one. It's the K at the end of Facebook and the TH at the start of thank you. So we note that. And by the way, the fact that we've wound up with a symmetric arrangement of the total Z1 count being equal to Z6, Z2 to Z5, etc., that's just an artifact. It just happened this way. It's not necessarily typical. Let's step back a moment and take a look at what we've got. We've counted out the actual triplets for a really simple little text string example for the one-dimensional cluster variation method. Now, to the best of my knowledge, this is the first time that anybody has put together a demo of calculating anything for the cluster variation method in particular detail like this. Let's take a look at our little table here. Once again, it's symmetric. That's just an artifact. We don't expect it to happen every time. What we want to note are the probabilistic expectations for the various z values versus the actual count. In other words, if the triplets occurred in sort of a random coin toss manner, we would expect, for example, 0.125 as a fraction of the z1s. But it turns out that we actually have much fewer than that. What this is telling us overall is that we're getting far fewer of the vowel triplets and the consonant triplets that we would expect. We don't have that much gluing together of like near like. That's a little odd. Similarly, we see a little bit too much of a preponderance compared to the statistical likelihood for the alternating ones, a vowel consonant vowel or a consonant vowel consonant. It tells us that the interaction enthalpy parameter that governs the gluing togetherness, so to speak, of our like near like elements is low. It will likely be less than 0 after we work everything out. So let's give ourselves a little bit of homework to do between now and the next video in this series. First of all, let's compute those y sub I values, y1, y2, y3. Remember that y2 is going to be degenerate, just like z2 and z5, so you're going to want to count it 2 different ways. That's going to be an easy one. It's just the nearest neighbor on the diagonal. Very easy to do. Secondly, let's compute the entropy for the 1D CVM for this example. We can use the equation that I gave earlier. Here it is again. Now our third step is where things get kind of interesting. We consult the pre-worked analytic solution for the 1D CVM. And this solution is worked out only in the case where you have equal numbers of on and off nodes, that is, equal numbers of consonants and vowels. The analytic solution is actually a set of equations, each giving an equation for one of the configuration variables, such as z3 or z1 or y2, as a function of the interaction enthalpy parameter. And here we're creating a function of that interaction enthalpy parameter itself. We're calling it an h value, which is a function of epsilon 1, the actual interaction enthalpy. Here's what one of those equations looks like. I'm showing it for z3. So as an exercise, let's go back to that table that we created and take a couple of our z values and put them onto that analytic solution. I'm showing this for z1. You do it also for z3 and y2 as well, since you'll be computing that. We'll compare results in one of the follow-up vids. You don't have to be terribly precise. We're just doing back of the envelope work today. We'll invoke some computer programs a little down the line. What we want to be asking ourselves is step 4 in our homework, which is, do these various configuration variable values more or less line up in a vertical line? That is, do they correspond to approximately the same h value? When these configuration variable values line up, then the system is at equilibrium for that particular h value or that particular interaction enthalpy parameter. This isn't always the case. I think that we will be there today because this is a fairly simple example and it's just falling into place very nicely. But we'll find a lot of examples as we go down the road where a system is not at equilibrium. We have the various configuration variables that we plot onto the analytic graphs are all over the place. There's quite a distance between their corresponding h values. In that case, we'll start to invoke some really interesting new processes that let us bring the model as close as possible to an equilibrium that is corresponding to a best match to the actual data. But that's a question that we're going to defer until later. So let's close with this for now. We've had a lot of fun, and we've gotten a really great grounding in how to work with a cluster variation method. A super good start for today. So thank you. We'll move on from this in our next video. Great having a time with you. Now is a very good time to start chiming in. Are you working through the equations, through the code? Have you tried this example? Are there questions? Are there things that you would like me to discuss in future vids? Is there anything where you'd like to provide some input? So we'd love to hear from you. Preferentially, please, although I love to have comments in the comment box on the YouTube, go over to the blog post and work from that base. And the reason to work from the blog post is I could respond to you briefly, but if you're asking something that requires a more thoughtful, nuanced discussion, maybe a diagram or two, I can go back into the blog post, edit that, and present that to you, and then we can enrich our conversations a little bit more. So thank you. Have a lovely day. We'll see you again soon. This is Aliana Moren signing off from Themesis Incorporated.